the kind of end goal is to be able to send out a fleet of robots, a fleet of surveyors, all different sensors, different modalities, and be able to come back and tell us what they've seen.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. To propel our nation to new heights of scientific and economic achievement, an unwavering commitment to driving American innovation is essential. We are joined today by Katie Skinner, an NSF-supported assistant professor whose group researches robotics, computer vision, and machine learning to enable autonomous exploration in remote environments such as space or underwater. Their work is advancing the field of robotics by combining computer vision with the advances in machine learning techniques AI affords. Dr. Skinner, thank you so much for joining me today.
Thank you for having me. I'm excited to be here.
I'm excited to talk to you. I want to hear about this data set that you have out there, AI for Shipwrecks. What is this?
So my group focuses on robot perception in field robotics applications. So this is anything from air, sea, space applications. The AI for Shipwrecks dataset is a new dataset that we have released for shipwreck detection from Sidescan sonar imagery. So this dataset is something that we have collected over the span of 5 weeks across 2 years in Thunder Bay National Marine Sanctuary, which is a really unique environment up in Lake Huron. There are 100 known shipwreck sites up there and 100 suspected shipwreck sites. So our project, which was funded by NOAA Ocean Exploration, our goal was to go up, collect a large data set of these shipwreck sites with an underwater robot, and use this data set to develop machine learning models for shipwreck detection from the sonar data.
What are the limitations with mapping or visualizing underwater?
Sensing is quite different underwater than we're used to on land. So, on land, we're used to using cameras to get really dense color reconstruction. Underwater, the process of underwater image formation is actually quite different than on land. So we have underwater effects like attenuation and backscattering, and these can lead to degradation in images that we see underwater. So if you've ever taken a picture underwater, maybe diving, you may have seen this, that the images that you get back are blue or green in color, and they might have a very strong haze effect across the image. So because of these effects, we have a couple of operational challenges. One is that we actually can't image very far away from the vehicle that we're working with. So typically we do imaging surveys about 2 to 4 meters off the seafloor or the target of interest. And it also can be quite challenging to process this data once we get it back on land. So a lot of the methods we use in robotics for mapping, for example, were developed for imagery we collect in air, and they don't necessarily translate directly to processing these underwater images. So this leads to challenges both in data collection and also data processing.
Does that depth of field create a problem with the shipwrecks that might be variable? Like, do you have to really be on top of kind of the height of them?
One challenge, of course, is we don't want to disturb the site. So if we need to be quite close to it, we actually, to perform autonomous missions, would need a very good level of autonomy in order to perform safe planning and safe surveys of the shipwreck and maintaining a safe distance while being able to capture useful images. So one option we have underwater is actually to use different types of sensors, like acoustic sensors. So acoustic sensors are using sound, and they're widely used underwater for communication as well as for imaging and mapping. So acoustic sensors have a much longer range than we get from camera imagery. So we can actually be a good distance off the shipwreck. And this is what we have been focusing on for the AI for Shipwrecks dataset, is actually using sonar imagery so we can carry out large area surveys a good distance away from the shipwreck to do that initial detection. And that initial detection would then be used on board the vehicle to eventually autonomously collect imagery in close range.
What are some of the limitations with autonomous underwater vehicle perception in general?
AUV, or marine robot perception, is a really interesting field. So a large part of my work focuses on this area. And it's has quite unique challenges. I think aside from the underwater effects that we mentioned on, camera imagery, other sensing modalities that we're used to working on land, we also don't have access to things like GPS and Wi-Fi, right, that are very widely used on land. So this leads to very interesting research challenges, of course. Now we have to develop mapping methods that don't rely on having known location. So a lot of our work focuses on addressing kind of these open challenges. But aside from those theoretical challenges, there's also just a lot of operational challenges. It's very expensive and time consuming to collect data underwater. It can turn quite dangerous, of course, depending on the weather and the conditions. So these are all things that make working in the field both challenging, but also can be pretty exciting too.
Thinking about that sonar, what is side-scan sonar?
Sidescan sonar is a widely used sonar sensor. It is an acoustic imaging sensor, and they're of use to us in our marine robotics lab in particular because they're a pretty small form factor, so they can be mounted on board an autonomous underwater vehicle. So it features two lenses, one on either side of the vehicle, that image out on either side of the vehicle and return acoustic intensities, so we can build a side scan sonar image from this return. And there's, a couple of interesting things about working with side scan sonar data. The images, look, of course, quite different than we get back from cameras. There are some very interesting shadowing effects. So you're not able to image something maybe behind an acoustic ping that goes out and gets returned. So with the shipwrecks, especially if there are sites that have very high relief off the ground, we get some very complex shadowing effects, which are quite interesting to work with.
What are some of the limitations with using sonar?
In general, sonar can be quite sparse, of course, compared to underwater imagery, and it can be noisy as well. So you have to have very good localization of your vehicle or an estimate of where the vehicle is to get a good image in the end. And in general, there's a lot of work on land processing images or processing other sensors like LiDAR data. But due to challenges with access, challenges with operations, how expensive it is to collect underwater data, there's in general just much more limited work and much more limited data available to work on these topics. So this can be one challenge for furthering research in the field of acoustic image processing or using acoustic data for robotics applications.
Taking that data and moving it into the lab or into the computer
Mhm.
situation, what are some of the challenges translating that into something that's useful for machine learning applications?
For machine learning, the state of the art or methods that perform the best are supervised methods. So these supervised methods rely on a large training data set to actually learn how to go from the input image to the output that you want, which in our case is a segmentation or detection of a shipwreck site. So on land, we have data sets available from autonomous driving applications, for example, that have thousands, tens of thousands. In some cases, for some tasks like ImageNet, we have millions of images, right? Underwater, that is not quite the case. So we have much more limited access to data and especially limited access to labeled data for carrying out supervised learning. So one of the goals of this work was not just to collect the data set, develop machine learning methods, but to actually release the data set to the public as one resource to continue investigating some of these machine learning challenges. So, because we have more limited labeled data available, our work in our lab actually focuses on how we can develop machine learning models that don't need quite as much access to labeled training data. So, we use things like simulation engines to develop simulated side scan sonar imagery that we can use to help kind of augment our real data sets. And we also develop machine learning models that can perform training with self-supervision cues. So we have reduced the reliance on labeled data for this task.
Thinking about having that data be public, why was it important to make sure this is accessible to other parties?
Yes, I think especially with all of the interest and excitement around AI, it's really important to make sure that we're casting a wide net in terms of where AI can have impact. I think that AI is really exciting right now and has a really large potential to have impact in marine engineering, marine science applications. And of one of the barriers, as I've talked about, is access to labeled data sets for training. So I think the main goal here was to kind of reduce the barriers so that more people, both in the public and the research community, could start to work on these problems, and that would really help to accelerate innovation in ocean exploration and in marine applications.
How did this dataset join the National Artificial Intelligence Research Resource Project?
I had heard about the National Artificial Intelligence Research Resource, or NARE, and was really excited about the potential to help kind of broaden participation in AI for this space. So, one of the goals of the NARE project is to facilitate uh, providing AI resources like data sets and also software support to a broader community. So I had submitted this data set for the NARE pilot program, and it was accepted recently. So we're really excited to be on board for that pilot program to see how the NARE resources can help to accelerate access and interest in this space.
I also want to ask you about your career award. How has NSF support impacted your career overall?
So I recently received the NSF Career Award for early career research, which has been really exciting. And that work actually is related to our shipwreck detection work, in that the shipwreck detection project first focused on sending out robots for large area surveys to detect new sites. The work for my NSF Career Award will focus on the aspect of, once we have those detections, how do we actually perform underwater imaging surveys in an efficient way so that we can build 3D models of the shipwrecks that we're seeing in real time. So the NSF Career Award has been really integral for enabling us to tackle this really challenging research problem that has been an open challenge in the field of how do we perform real-time dense 3D reconstruction underwater.
What are you excited to work on next in your work yourself?
So I'm really excited about work we're doing right now to actually perform multi-sensor fusion of sonar and camera imagery. So I think this is an interesting challenge that has been focused on in the research community, and we're looking towards this now through our work with their NSF Career Project for shipwreck mapping. So I think that's a really exciting avenue. I'm hoping that we'll have some nice new data products, 3D models of shipwrecks to show in the future.
So for my last question today, I want to ask you about autonomous surveying in general and the future of it. Do you think we'll eventually be able to get all of the ocean at high resolution and make other amazing discoveries?
That's the goal. That's kind of my dream and vision, especially working in marine robotics. I think, the kind of end goal is to be able to send out a fleet of robots, a fleet of surveyors, all different sensors, different modalities, and be able to kind of come back and tell us what they've seen. So whether that's mapping, but also new discoveries of shipwrecks or other things we might find underwater. I think that's really the ultimate goal. And of course, there's a lot of work to be done, but that's what that's what we're here to do.
Special thanks to Katie Skinner. For the Discovery Files, I'm Nate Podker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.